I'm Jared Robinson. I've been using RabbitMQ for a year and a half, 2 years, something like that. Work for Vivint. How many of you use Rabbit right now? Okay. Do you use Rabbit?
Yes.
Okay, great. How long have you used it?
A little bit for a couple of years.
Okay.
For OpenStack.
Okay, great. So if you have thoughts or feedback or insight, you're welcome to share it. Ask me questions. I may not know the answer to everything because we use Rabbit for very specific things. We don't use all of its capabilities. So this is Kelly. It's one of my coworkers. He works on the ops team. He monitors Rabbit for us and configures Rabbit, and it's been good. So he's going to handle the slides for me. I've got my printout. If you go online, here's the URL down there too. You can follow along. There's notes in the slides. If you hover over this down at the bottom, go ahead and hover over the bottom right there, Kelly. Yeah, so if you hit that little O, it goes into like notes mode, and you can see all the notes and everything. So I've got 5 awesome children. They're usually awesome, sometimes not so much. I like programming and solving problems. I'm not really married to any one technology. I like to use what works. I like Linux quite a bit. I was more enamored with it one time than I am now, but I still love it. It's my favorite OS. It's not to say it's perfect. Nothing is. And I enjoy working at Vivint. It's been a great ride. It continues to be a great ride. Work with great people, and we're doing cool stuff. We use MongoDB, we use Rabbit, we use Python, some Java, and other teams use .NET and other technologies. So I believe we should use good tools, but we have to temper that with use what's good and what works well, and given the time constraints we have. And so, in as much as possible, I like to try it, test it, and benchmark it. And if it doesn't work, brainstorm with other people, try something else, and fail fast. Now, that doesn't mean I've tried everything under the sun. Let's go to the next slide, Kelly. Oh, I haven't gotten to that slide. So I haven't tried Kafka. I haven't tried ZeroMQ. I don't know how well those things work. I don't know if they're better than Rabbit. Rabbit's a very mature, in a good way, type of a tool. It's still very well maintained. It has a great community around it, and it's worked well for us so far. So how many people don't know much about Rabbit or messaging? A couple of you. So we could cover the basics of some of that stuff. Let's go to the next slide, Kelly. Next. Oh. We'll talk about what's not covered here. This is good. So I'm not going to talk about publish, subscribe, although Rabbit does that well. I'm not going to talk much about topics. Probably won't talk about topic subscriptions at all, or RPC. Rabbit can do all of those things. I'm going to talk about direct queues and about how to configure Rabbit. So let's go to the next one. So what is Rabbit? It's a messaging broker. What does that mean? What do brokers do? A mortgage broker simplifies our life. So if I'm going to get a loan, I don't have to go out there and go to every single place that might give me a loan. I go to a broker, and that person goes out and talks to all the different people who give loans and figures out which one will give that to me and gives me the different options. So it simplifies my life, and so that's why we use RabbitMQ. It's a broker. We use it for messaging. RabbitMQ is great because it has clients for every language under the sun. If they have like first-class support for Java, .NET, and C or C++ because they actually maintain the drivers for those languages. But there's like 3 or 4 Python drivers. I don't know how many there are for PHP, but there's drivers in every language you can imagine. RabbitMQ is based on the AMQP spec as much as they can be. And so that means they have interoperability with other AMQP libraries. They support other protocols besides AMQP, like Stomp, and there's some other one too that I don't remember. We don't use those. We just use the AMQP stuff. So who doesn't know what an exchange is? I see one hand. So an exchange is, you come somewhere, maybe you're going to go to a big bazaar where people are selling stuff, and there's tables. Everybody that wants to sell jewelry is at one table. That's like your exchange. You might say, hey, I want to buy a necklace, and a whole bunch of people might be able to service that request. So the exchange is kind of like a bit of logic in Rabbit. You publish to an exchange, but it's just logic. That logic is distributed throughout the cluster, and it tells what queue to go to. The queues say, hey, I'm interested in servicing jewelry requests. And the Rabbit server keeps track of all the queues that might care about that, and it can publish your request appropriately. I had an analogy with post offices and messages too. When I publish a message, I might want to broadcast it. I don't want to have to know every single person downstream that's interested in that message. Rabbit abstracts that away. Or I can go direct. Maybe I want to send a message to my brother who lives in Roy. And I just send it to the post office and it gets there. I don't even have to care that it's going to my brother. It might be that I want to send a message to somebody and I say, you know what, I have a message that's going to go to one person and it's regarding my rent. I don't care who it goes to, but the post office is going to figure that out for me because Rabbit has all the logic wired up by the consumers on who should get that message. Rabbit has a concept of routing keys. So when I go to pay or to buy a house, I have to pay earnest money to someone and to say that I'm really interested in that. Well, I don't really care who that goes to. The middleman takes care of that for me. They make sure my check gets to the right person. So I can label my message with, hey, this is earnest money. Somebody else takes care of that. They route it for me. Same kind of concept in Rabbit. Rabbit also has connections and channels. This is a concept I didn't understand at first. So you have a TCP connection to Rabbit, but you can have multiple channels that use the same TCP connection. That can be handy if you have multiple threads. They all want to use the same TCP connection. You can do that. And we use direct exchanges, which means that there's a, well, what does it mean? We use work queues, and Rabbit doesn't really have a concept exactly like a work queue, but you use a direct queue as a work queue. So let's go to the next slide, Kelly. So what we do is we have actually multiple publishers. They all publish to one exchange, and it goes to a single queue. At least this is historically how it worked. And then we have a whole bunch of consumers that distribute that work, and we can scale that according to our needs. Welcome. And historically, that was around robin distribution. So we would publish messages. Say we were publishing history messages, and that would go round robin to all of our consumers. And in the beginning, we used some of our queues as persistent queues, some of them as transient. How many of you use persistent queues? How many of you don't? How many of you use transient queues? So most of you are using durable. So we've chosen to go completely transient in the last few months. I'll talk more about that, I think, later. Let's go to the next slide. Oh, question?
So you're using message broker. What's the purpose you're using now? What you're trying to accomplish?
Oh, so what we're trying to accomplish is to build a scalable system. So we have a whole bunch of computers running a whole bunch of processes, and they're all grabbing work to do. So most of what we do is we have security panels that send signals to our backend system. That goes into queues, and then we have a whole bunch of consumers that service those queues. And so if we need more history handlers, we can just spin a whole bunch more up. We don't have to worry about getting those messages to the right place because Rabbit takes care of that for us. They just connect and say, hey, I'm interested in history messages, and Rabbit says, okay, I'll distribute some of that work to you.
Yeah, the durability is something which, the persistence one, how much that data that you need, even if there's some failure, and the capacity to recover it back and process it again?
Right, so the comment was that persistent, if you choose to go persistent, it's usually because you want that data to stay there until you're done processing it. Even if your Rabbit server dies, you want to be able to bring it back online and have that still be there. Yeah.
I mean, if there's any need to such extent, probably we should go persistent level. Otherwise, the message is something that's not that important. So even if it goes off, and we're fine to deal with that. Yeah,
so if you don't care about the message, it can be transient. In our case, my opinion is that if the person that produces the message can verify that it got delivered, the best place to persist that message and keep track of it is at the producer side. And so it used to be that when we started, all of our alarms were in a persistent queue, but it turns out our alarm panels, they know whether or not our platform has handled. We respond back and we say, hey, we've delivered that. And once we've delivered it, then the panel can throw that away. And if our intermediate infrastructure dies, the panel remembers and it keeps sending that. And so the persistence is at the endpoint instead of in Rabbit for us. And that allows us to go faster. Not that it matters a whole lot. Alarms are one of our lower volume queues. Let's go to the next one, Kelly. So if you want, you can come browse this book, or I can hand it around. Who wants to see this? Anyone? Will you pass this back? So I think this is a great book, RabbitMQ in Action. It's a couple of years out of date, but they wrote about things that were up and coming at the time. I think they have a lot of great advice born from experience. Reading through the Rabbit docs, you just won't get the kind of advice that you get out of this book. One thing that I noticed when I was reading this book, early on we cared about high availability. We had these durable queues. We wanted them to keep on working even if one of the Rabbit servers died. It turns out if you use normal Rabbit clustering, that can be a problem. And they talk about how to solve that. Let's go to the next slide, Kelly. We care a lot about latency too. When a panel says, hey, the door opened, it's nice for the mobile apps to show the user that that's happened. Or if the person using the mobile app says, hey, arm my system, it's really nice for them to know that that happened. So we don't want it to take 10 or 15 seconds. We don't want it to take 5 minutes. So we care about the speed of this thing. And like I said in the beginning, we used round-robin distribution. So Rabbit has this concept that when a consumer connects, he can say, hey, here's my prefetch size. And most of the time, if you don't specify that, it just doesn't happen. And so what Rabbit's going to do is, if every one of the people in this room is connecting to the Rabbit server saying, hey, I want to listen to the speaker, and he's sending me messages, and I'm going to start round-robining those messages amongst you. And if I have 100 million messages, I'm going to distribute that equally among every one of you. But some of you might consume those messages a lot faster. And when I have distributed work that needs to be handled quickly, I don't want a single slow consumer slowing down the whole system and backing up my queue. That's what we had at first. And so that prefetch is a really important thing. It also keeps the latency lower. So I think in the notes, I may have a URL to this, but there's a blog post that the Rabbit guys did on what proper prefetch sizes should be. And the best way to run Rabbit is to run it on your local LAN and not across a WAN link. And our latencies are really, really low. So the prefetch of like 1 or 2 or 3, it's just fine. And when you start having prefetches of like 100 or 1,000, that can get to be problematic, especially if a single message is processed slowly by a consumer. Oh. Oh, I don't know if I care about being in the video or not.
Well, good choice.
So things that can slow down your consumers, database lock contention, and we do a lot of interaction with the database. One thing that we didn't have great visibility into at first was some of the CPU contention. So from the VM's perspective, there was plenty of CPU available. But since it was virtualized, it turns out that there was some slowness going on because other CPUs were busy. And so once we started monitoring it on the outside, on the hypervisor side, we moved some things around to make it more efficient. Of course, if third-party services are slow, your consumers are going to be slow too. Use the right prefetch. Some of that doesn't matter. Next. Oh yeah, there we go. It's an example in Python. You can configure prefetch two ways. You can do how many bytes of prefetch you want or how many messages you want. And there's this global flag that tells it whether or not that should be the same across all consumers or not. We never use that. That way, if you want to tweak it and change it, you can, per consumer. Partially restart things as you go. Next. As I was experimenting with Rabbit, I found some interesting things. You can publish to an exchange that isn't bound to a queue. No errors. I don't even know where it goes. Does anyone here know where it goes? Rabbit has default exchanges. If you publish to an exchange of empty, it'll go to what they call the default exchange, and you can read from that. But I don't know what happens here. I don't know if it just goes into the ether. It's possible that you can set up a dead letter exchange for that and grab the messages. So what we do is all of our clients always declare the queues and the bindings to the exchanges. And as long as they use the same parameters as all the other ones, it'll work. If they declare a different parameter, like if they say, hey, I want to bind to this exchange, and by the way, it's not a direct exchange, it's a topic exchange, it'll throw an error when it tries to connect. Okay. So I said we cared about latency because we care about the speed of servicing our customers. So we know that fast hands are good, but that doesn't mean that it makes light work. And I thought Edward Scissorhand was a great example here because he's kind of a machine. We're dealing with a machine here that goes fast, or is supposed to go fast. When I first started, I read about HiPE, which is supposed to make your Rabbit server go faster. And I thought I'd turned it on. But it turns out, like 6 months later, I figured out that the CentOS and Red Hat stuff that uses Erlang doesn't have a version of Erlang that supports HiPE. So even though I told Rabbit to turn it on, it never got turned on. This is interesting. But without HiPE, I figured we could go about 10,000 messages per second. But we have to temper that with the fact that our Rabbit servers are running inside of VMs. So how fast can they really go? Well, 10,000 messages per second, as long as there's no other contention on that Hyper-V box. And Rabbit seems to really use the resources that are there. It uses Erlang, and so it uses all the CPUs that are on the box. Erlang doesn't care whether one of its threads or processes runs on one CPU or another. It's extremely scalable, I guess, or I don't know. It's very concurrent. So in my opinion, Rabbit works really well on its own dedicated box. That's not how we're running it, though. One question that we've had is, do too many consumers connected to a queue, does that slow Rabbit down? And I don't know. It seems like we felt like it did, but we've never done any real measurements to figure that out. So it's something to keep in mind when you're using Rabbit. Let's go to the next slide. So our needs. As of March, our busiest queue went at about 7,000 messages per second at peak times. So without HiPE, 10,000 messages per second just isn't going to cut it because we're doubling our size this year. And we want headroom. So how do we get there? Next. We're going to do sharding, or partitioning. And so the first thought was, let's use Rabbit's consistent hash exchange. This is a plugin that ships with Rabbit, so it's well supported. And it sounded like a great thing. So let's go to the next slide. It gracefully handles the disappearance of a queue. So we can put Rabbit in clustered mode. We can have queues on different nodes. If one node goes down, the exchange is fine with that. It'll just route the messages to other queues that are still there. It's nice because we wanted 3 downstream queues to handle our load. We can do that. We can even have a cluster of 4 or 8 or 9 nodes. We only have to have 3 queues. And another really cool thing is the Rabbit console shows the entire cluster. So you don't have to build your own tools for that. And the management console is fairly nice. Who's seen the management console? How many have not seen it? I'll have a picture of it later on, and I may show you that a little bit more. Okay, Kelly, let's go to the next one. So here's how I enable it. The UMask thing is really important if you're running it as root. We use Salt to configure Rabbit, and since Salt runs as root, typically, that was really important to get right. Otherwise, the Rabbit user could not read the plugin and enable it. Next. Consumers declare the exchange type as that, and they bind the exchange to the downstream queues. This is interesting. So the routing key, so you bind the queue using a routing key. And so for example, what we do is we say, I've got a history queue. I'm going to bind that to my exchange, and the routing key is history. And that's what we've typically done in the past. But with the consistent hash exchange, at binding time, you have to say my binding key is the number of points in the hash circle that I want it to be bound to. So they recommend that you use something less than 1,000, but that's the number of points at which it gets bound, so that if one of the nodes is lost, it kind of distributes it around. And the higher the number, the better, because it distributes it a little bit better. So it's called consistent hash exchange. And I didn't really think about that too much at first, but it is very consistent. If it delivers something based on one routing key, then the next time you use the same routing key, it's going to deliver it to the exact same queue the next time around. I wanted equal distribution. That's not what this does. So when you publish, the producers have to vary the per message routing key. So you can use a random number, which is what I tried doing, a uniform random number. Or you could use something like maybe a security panel ID or whatever ID that you have, a customer ID. Last note there, when you cluster Rabbit, this is just not really related to consistent hash exchange, but make sure that the firewall is configured to allow all the ports, because when Erlang servers talk to each other, they use a range of ports to talk, and you've got to set that all up. It's in the notes. You can see that if you want to. Who can see this? Is that readable? Okay, so this is my first test. I bound these queues with what I call it, the binding key of 2. Then I published, I think it was 100,000 messages to it. And you can see it's not equal at all. I've got 9,000 here, 46,000 there, 34 there. That's not what I wanted at all. I wanted to bind an equal number of consumers on each queue and handle my load that way. That wasn't going to work. So I used a larger binding key. Next slide. It's a little bit better. Still not anything like I wanted. Next. So it wasn't what I wanted. Let's go to the next slide. So we found something called RabbitMQ sharding. It's built by the Rabbit guys. Sounded good to me. As I worked through it, I discovered that it's built on top of the consistent hash exchange, so both have to be enabled in order to use it. This sounded really cool because it abstracted some of the things away from me. I could tell a consumer, hey, I want to connect to the history queue, and it would figure out which history queue had the least number of consumers and connect it to that one. That sounded exactly like the right thing to me. Doesn't ship with Rabbit. That's a little bit of a downside, but it's not hard to download. Let's go to the next slide. So here's how I enabled that. Next slide. Oh, let's go back for a second. So you configure these things using policy. Got my history shard, I'll go back to the... So this is the regular expression that says, hey, match anything that starts with history, and we're going to have 2 shards per rabbit node. And I chose a random key of 1, 2, 3, 4. It's a similar thing, kind of like the consistent hash exchange there. And so the plugin manages how many queues there are per node. Next slide, Kelly. When clients connect, they declare the exchange type like that. And so we can configure the policy before any exchanges exist. When you declare the exchange, the policy will be applied, and then it does the right thing. It seemed pretty good because it had equal message distribution. When nodes appear and disappear, it goes and creates those queues automatically for me. If I will, and I manually use the admin console to go and delete a queue, it's gone. It doesn't route messages to it anymore. But as soon as a new node comes online, it recreates the queues across all the nodes, even the ones I deleted. Next slide. This didn't seem like such a great idea. Losing messages when I'm binding or deleting a queue. We do that every once in a while. But it turns out the consistent hash exchange had that same problem, and it's based on the consistent hash exchange. This is more of a kind of a side note. So when producers are publishing to the queues and one node fills up, producers block. Now, with this one, you wouldn't expect that to happen. You'd think, oh, I'm publishing to an exchange. Rabbit should just handle that if one of the queues goes offline. But what we have to remember about Rabbit is that an exchange is just a piece of logic. It just says, hey, if you have criteria that matches this, I'm going to put it in this queue. So a publisher is putting it into a particular queue, and if that queue is blocked, and that happens to be the one I'm assigned to go to, your producer blocks too. Unfortunately, we had a cluster of several nodes. I didn't really need like 5 separate queues to handle my load. I didn't want to have to connect consumers to all of them. So this wasn't really the solution we wanted either. Let's go on. So I mentioned connections and channels earlier. This is just a side note. This doesn't have anything to do with sharding. Initially, we were using one TCP connection for every single guy that wanted to connect to the server. I changed that a little bit when we implemented our client-side sharding so that we use one TCP connection and we have several channels in use by that. It seems to work out well for us. There is advice on the internet that says it's a good idea to keep your publishing and consuming connections completely separate. That way, one doesn't block behind the other. Go ahead, Kelly. So we decided to implement our own client-side sharding solution. That means more work for us. But one thing I may not have mentioned earlier is that queues only live on a single node. And with the consistent hash exchange, you have to connect to a node. And when your client connects to that node, it can declare the queue. If the queue doesn't already exist, it's going to be created on that node. You can connect to any node in the cluster, and you can read from the queue, you can publish to the queue, and it will get to the right place in the cluster. Rabbit will do that for you. But the queue lives on one node. So in order to get the queues spread across the different nodes in your cluster, you have to connect to the right place to create them in the first place. Well, client-side sharding had to be intelligent enough to do all that. It seems like, regardless of whether we used RabbitMQ sharding or, client, that consistent hash exchange or client-side sharding, we had to have enough smarts on the clients to connect to the right node to create the queue where we wanted it to be. So why don't we just go with client-side sharding? We had to do a lot of the same work. So there are some advantages for us with client-side sharding. We could have shared nothing Rabbit nodes. It needs a little bit less management from our ops team. They don't have to go and make sure that the the cookie file that allows different nodes to connect together and talk to each other. They don't have to distribute that on every node. Not that that would have been a big deal. But if a single node in a cluster disappears, the cluster knows about that and wonders why that cluster is gone. Well, the node is gone. And in this case, if we have shared nothing, a node disappears, the cluster doesn't care, and our producers go on with life. Downside is we have to implement it for each of the languages we use, and we do use more than one language. One big plus is it gives us failover. We don't care if a node goes down, but we do have to plan for capacity with that. What I mean by that is that if we have 50 consumers spread across 3 Rabbit shards, and those consumers are busy and really busy, and one shard fails, our clients are sticky. They stay on one node. They don't reconnect to a different one. And so we have to have enough capacity that the remaining nodes can handle the increase in traffic. So let's go to the next slide. Our producers produce messages round robin. So I talked about how round robin was bad early on and how a prefetch changes that, makes it better, but now we're back to round robin again. It's not quite so bad because we've got a whole bunch of consumers on each queue. But we have seen it sometimes get a little bit out of balance. Usually doesn't last for long. Our consumers have to decide which shard to connect to. Initially, I thought, we'll use a uniform random distribution to connect. But it turns out that that wasn't very uniform. It seems like we had to restart handlers a lot to get them uniform, so we didn't use that. So now we have a separate configuration file that tells it which shard to connect to per host. Ideally, we would use the RabbitMQ management interface, it's a REST interface, to go out and traverse the nodes and figure out which shard has the least number of consumers and connect to that one. We'll probably do that at some point, but the reason we haven't done it so far is because it's complicated. Rabbit only updates its stats like every 5 seconds, and so if you're restarting a whole bunch of consumers at the same time, they're going to swarm on what they think is the least busy queue, and then they're all going to be on the least busy queue, and none of those are going to be serviced. So you have to keep that in mind. Let's go to the next slide, Mike. So I mentioned earlier that the RabbitMQ in Action book talks about how to handle durable queues in a high available scenario. What they recommend is that you have shared nothing servers, and if you are using, if you're not using your own client-side sharded stuff, probably want a load balancer in front of that, and the load balancer would have one Rabbit server that's shared nothing, be the primary, and the second one is the secondary. And if the first one isn't available, then your traffic would go to the secondary. Because what happens is when a durable queue goes offline inside of a cluster, it's not available. You can't recreate it on any other node. That's bad. We didn't want that. So plant-side sharding helps us with that too. Of course, as I mentioned earlier, we don't use durable queues anymore. I'll go back, Kelly. Another nice benefit of shared nothing is that we can mix and match Rabbit versions if we want to. So if we want to upgrade a single Rabbit node to a newer version, we can do that, and we can gradually go through and get that done. We usually keep them all the same version though. Downside here is that the RabbitMQ management console doesn't show us all of our queues in one interface, so we had to write our own. This is an approximate mock-up of what we have. Works really well for us. One thing that we like about writing our own plugin is we can see some of the things we really care about. Typically with the Rabbit management plugin, we had to drill down to see things like the consumer counts and the utilization. Now we can see exactly how many consumers are in each shard. That's very useful. We can tell how long it's going to take to clear out a given queue, or we're having problems. We have no idea stuff help us alert on that stuff too, but it's nice to look in one place and see it all. I'm going to talk about this for a second. Consumer utilization. This is a new feature that Rabbit added in, I think, 3.3.4. something. And it's kind of backwards from what you might expect, but 100% utilization just means that Rabbit doesn't have to wait for the consumers at all. That's a good thing. You want 100% utilization. If you're down at 1%, it means the consumers are going really slow and they're not ready to accept the queues. Now, for some of our queues that we have, that doesn't matter. Some of them we expect to go slow and we expect them to decline slowly. But for most of them where we want low latency, we want that to be 100% at all times. Now, we also want to know how many more handlers we have capacity for at any given time. So we have a separate, we use scalable, and our consumers will, they measure their idle time versus how much time they spend processing. And we look at the idle time and we say, hey, if the idle time drops this below a certain amount, we know we need more consumers so that we can handle failure. So those are the caveats. As with RabbitMQ sharding, if a single queue blocks, and we're just round robining, that single queue will block us from publishing to any others, and that can be a problem. The MQP specification, I think, I don't know this for sure, but at least with the libraries we've used so far, when you produce or publish a message, that is a blocking call. It doesn't return to the caller until it's published. And that's their form of flow control. Next. So this is something we haven't explored too much yet. Federated queues. These have been there for a while. I say a while, maybe a year or two. So federated queues are, okay, there are two things. There are federated exchanges and federated queues. I'm not talking about exchanges, I'm talking about queues. So the cool thing about queues is that you can publish an upstream and several downstreams can all grab from that queue. We still care about locality. And that's one advantage that the client-side sharding gave us is that we publish the same Rabbit service it's going to be consumed from. It doesn't have to make its way through the cluster. Federated queues may not be the ideal thing if you want that locality, if you want optimal network performance with your switches and everything. You want traffic to go exactly where it should. It's cool because you can mix and match Rabbit versions. It's kind of like, it's like another consumer almost. It just uses a library to go and pull those things down. Let's go to the next slide. So my thought is, wouldn't federated queues work really well with the consistent hash exchange? So early on I said, yeah, it doesn't distribute things consistently. And I want consistency. I want an equal distribution. But what if I hooked up sharding? And I said, okay, I've got 3 downstream queues. And these guys are also connected up using federation so that if they run out of messages, they can just pull from the other guy's queue. And the same thing goes with our client-side sharding. If one of the queues gets a little bit slowed up and it starts backing up, wouldn't it be nice if the other queue can just borrow messages and hand them to consumers that are ready to go? So that might be a future improvement. Next. Interesting fact there. Next. Okay, so again, early on when I came to the company, we weren't even in production yet, and we had, when we started, we had an early production system for our beta test. Rabbit started having problems because it didn't have enough file descriptors, it couldn't run enough processes. And Rabbit runs on Erlang. Erlang makes a lot of use of CPUs and stuff like that. Threads. So that's the default on CentOS. It wasn't what I wanted. So here's what we did. Increased it. That's not good enough for everything we've done so far. Next. You can't read from a queue that doesn't exist. You will get an error. I found out that there are some interesting things you can do if, for example, a queue is balloonning in size and there are no consumers. You can set up a TTL and dead letter exchange. We use TTLs on some of our queues just to clear things out that don't matter. Some of our messages don't matter after 30 or 60 seconds, and so we put a TTL on there just in case they get backed up, the old messages get deleted. But if you had a case where you didn't know if you were going to have consumers or not, this might be a good thing for you. Set up the TTL and a dead letter exchange. Next. I have mentioned this already. Disaster planning is important. What happens when a single node dies? We've had that happen. It wasn't Rabbit's fault exactly. We've actually had a few cases where Rabbit died. One of them was a kernel panic. Another time, it just got backed up. Let's go to the next slide. Okay, we talked a little bit about transient versus durable. I expressed my opinion earlier that the best place to persist messages is the guy that's producing them. Especially if you have a distributed system like we do. We've got hundreds of thousands of security panels. Why don't they just keep the messages until they can be sent? Transient is faster than durable. With durable messages, as soon as Rabbit gets them, it persists them to disk. That's not to say that transient messages don't get persisted to disk, though. If the queue starts getting backed up, Rabbit does push them out to disk because Rabbit doesn't want to run out of memory. Rabbit's fastest when there's no messages in the queue. Let's go to the next slide. We'll get back to some of that transient versus durable stuff in a minute. Now, did you know that a queue can be bound to multiple exchanges? Or the same exchange multiple times with different keys? I didn't know that. It's because we always use direct queues. We always use the same routing key. Simple stuff. You can't do stuff like this. So, even with direct queues, QA and QB can both bind using the same routing key. That's fine. They'll both get the same message. Let's go to the next one. Okay. So Rabbit uses, it has flow control. So when it gets busy, it blocks publishers from consuming until it's ready for more messages. Right? Not from consuming, but from producing. So what if you don't want a producer to block? What do you do?
You put more boxes.
Putting in more boxes won't help. Your producers block them publish into a single queue. In some of our cases, we have a single producer that's trying to produce to multiple queues, and we don't want it to block, so what do? Are we out of luck?
Can you proxy it? Can you put something?
Proxy it? Yes, so that's basically what we've done in some cases. So we have a separate thread. We publish an in-memory queue, and the separate thread publishes to Rabbit, and it caches to disk. Okay, so Rabbit monitors the disk space for persistent queues, and as I said, as soon as it gets a message, it tries to write it into a storage. But for transient queues, it also writes messages to disk when those queues start ballooning. And I've seen it crash Rabbit a few times. I mean, it's a bad state when you start getting really backed up on the queue anyway. It means there's a lot of latency for customers. It's not a good thing. And when we restarted Rabbit, it doesn't clear out that disk space either. So here's where it stores the messages. We'll remove the messages from there. So how do you keep it from sticking stuff in disk? For a bunch of Googling, I found that. But if you do that, it means it stores things in memory and it doesn't persist much in disk at all. And then you don't have as much runway. You can't use Rabbit as a temporary storage tool like you could before. So there's different trade-offs. Why does it crash? I don't know exactly, but I think it's because with transient queues, it accepts it into memory first, and then it tries to write to disk, and instead of disk space, then it doesn't know what to do. So that bug, I don't think has been fixed yet. I don't know if they will fix it. Another piece of advice that's in that book that I mentioned and is on the internet too is you might be able to get faster throughput by combining multiple of your messages into a single Rabbit message. But it does increase latency, which may or may not be what you want. We did some experimentation with that and it seemed to help. We didn't go with that as our solution though. We used Sharding instead. Next. So in summary, definitely use prefetch. If you're not using it now, or if you plan to use Rabbit, use prefetch. I think HiPE's a good idea. We didn't end up using HiPE because sharding got us where we needed to be. We had to scale horizontally regardless of whether we got HiPE working. So we may do that in the future. Plan for failover before you get into production. And definitely get your limits set correctly if you're in Linux. On Windows, I have no clue how it works. Next. And again, use good tools. I don't know if Rabbit is the best tool for the job. There are other tools that are out there. I looked at the ZeroMQ ever so slightly. Sounds like it's a great low-level library, but you have to build your own broker out of it. Questions, comments, advice? Greg?
What sort of situations would it be actually better to use like a high prefetch account?
Where you don't care about the latency, and if you're using it over, say, a WAN link, then you might want a high prefetch account. They recommend not to use Rabbit over a WAN link, and they have something called a shovel that you can use instead, where you have Rabbit in, say, one data somewhere, one location, and another Rabbit somewhere else, and you can use shovel to just move data. Questions?
You said that a producer cannot produce to an exchange that does not exist. Well, you can, but it returns no error. But you can't, the consumer can't go to an exchange that is not defined.
A consumer can't read from a queue that's not defined. It will get you in there. Yeah, so I want to mention something that I think, and I don't know why, but you triggered my thought. I mentioned earlier that we have our consumers, they're sticky on a single shard. Once they pick a shard, they stay there. Well, we can figure them out. They never move. Even if the shard's not available, they never read from the other shards. And that's not ideal from a capacity sense, because if you lose a node and all the messages are going other places, you still want to handle all that. But then you get into a chicken and egg problem where if the node comes back online and then the producers start producing to it, you need consumers there to start reading from it so you have the latency. Anything else? Well, thanks for coming. I didn't mention this before, but Rabbit is supported by Pivotal. Pivotal does consulting, so there's really good commercial support available for it. We haven't used that, but if that matters to you, that's available.